Good morning. Thank you. I'm Brian. I'm from Akamai. I'm responsible for the security of all of Akamai's deployed systems. All the 250,000 or so computers that Tom was talking about out on the edge, the cryptographic protocols. And an important element of making those safe is changing the world so that they can operate safely. So I've spent a chunk of the last couple of years working with the IETF, the Internet Engineering Task Force, on what's going to be the next generation of security protocols for all of the computers that all of us use. And I'm here to talk today about TLS 1.3, which I expect to be the standard for the next 5 to 10 years of cryptographic advancements for the internet. Maybe less, maybe more, we'll see as we go. What I hope to persuade you of today is that you can begin testing and operating with the new version of TLS in your systems, at home and in your jobs today. Not tomorrow, but over lunch, you can SSH into a machine, run a few commands that you're going to copy down from slides up here, and try out some TLS 1.3 right now and see whether your systems are ready to make that jump. Perhaps I will also persuade you that you should and could come to Prague in a couple of months, to Montreal a few months after that, and have some input into some of the extensions that are coming to TLS over the next little while. We're going to spend the next half hour reviewing what TLS is, where it came from, running through some of the bright points and some of the disasters that led to the shape that TLS 1.3 is today, run through how you might do some testing yourself, and then look at where the IETF is, and I'll invite you to come and throw questions at me towards the end. So who here has been using TLS and SSL since it was SSL, since, say, 1995? Can I get a show of hands for folks who had some involvement in the 90s? That's when I started. I had a summer job in 1996 providing a library for a particular scheme implementation for some AI researchers who thought that they had this idea that they could use machine learning and AI, remember, this is 1996, to model human behavior so as to make better purchasing recommendations. Now, their actual tech didn't go anywhere, in part because their student employees over the summer had terrible productivity. But SSL started in 95 and 96, and the OpenSSL library even started in 96, because people were starting to realize we could use the internet for commerce. Some of that first 5 years, right, from when Tim Berners-Lee is producing the first versions of the web in 1990, that version, every web server had a put command right next to the get command, and everybody could freely edit pages in those earliest versions. Could you imagine if we still had that working? If every web browser had an editor right there next to the browser, and that still worked that well, like everything's like Wikipedia level editable? Some of our intranet technology works that way, and oh my gosh, it's a nightmare. If the whole world were that way, wouldn't that be fantastic? Maybe someday. So 95, 96, we start seeing the first inklings of development. Now, you won't see SSL 1 on this timeline. Does anyone know why? SSL 1 was so bad, it got produced inside Netscape, and they reviewed it internally, decided it was a horror show, and threw it away. It never shipped to customers. It never made it out of beta. And so SSL 2 is what actually got shipped. Now, if you notice, the shortest gap on this timeline is between SSL 2 and SSL 3. That's because SSL 2, when Netscape put it out there, they released their server, they released their browser, the Netscape communicator, and they released a short technical note. And you can read on the mailing list where this initially got discussed, academic cryptographers reacting to SSL 2. And their reaction is basically, holy cow, I gave you people a degree? It had been some of the students of some of the academics who developed SSL 2. And, you know, I think they were busy trying to get Netscape launched. They had their startups in mind. They may not have been taking precise notes in the classroom. And SSL 2 makes a number of, you've got to be kidding me level, disastrous mistakes. Right? Now, who knows when SSL 2 got finally really scraped off the internet to where nobody's plausibly running it anymore?
Still hasn't happened.
It hasn't happened yet. That's right. I still have a couple of devices. There's some Ricoh fax machines that still will only use SSL 2 for updates. I've still got a couple of video game consoles that will only run SSL 2 and you can't update them. Now, The larger server operators will no longer run SSL2 for anything. But there is still, if you tap at a core point, you will still see SSL traffic on SSL2 traffic on 443, on 25, on a handful of other TCP sessions. Mostly it's moved on to SSL3, right? Okay, 96 was a great year. HTTP 1 is standardized, SSL3 comes out, and everything's good because these protocols are so great, nobody sees a need to update either of them for 10 years. What were we thinking, right? If you look at the developments in cryptographic protocol analysis between 96 and 2006, TLS1's ignorable, right? Because that's just relabeling SSL3 with minimal, if any, changes. There's not only are there huge advances in research, there's huge research increases in attack research. It's shocking that we don't see major updates. And when 1.1 does happen, it's basically ignored, right? Has anyone here actually run TLS 1.1 in a production system? I've never met anybody outside of Microsoft Research and a couple of weird DoD folks who shipped 1.1 right then who ever actually used 1.1 for anything. Everyone ignored this, right? The libraries didn't even push it until 1.2 came out. It's made available, and the libraries push it, but the clients are still ignoring it. The servers are still largely ignoring it, and you end up with crazy fallback dances. It's only in the last couple of years that the standards bodies seem to have woken up and realized we need to change our marketing strategy, and that leads to HTTP2 and TLS 1.3. So let's talk about why they woke up and who was pushing that. A huge chunk of that has been the large operators, people who are now pushing. Tom talked about pushing 60 terabits instead of 1 terabit per second over the last decade. The changes in the amount of business and money that are moving through the internet have been comparable, right? Multiple orders of magnitude more euros per day transacting through the internet now than 10 years ago. And that, again, orders of magnitude over 10 years before that. Before that, I think you run out of euros. But the big site operators, Google's logo's up here because they've been hugely involved in the standards process. But the Googles, the Facebooks, the Netflixes, the Amazons, the Akamais, the people who are doing trillions of dollars a day in business to consumer business over the internet have been pushing a huge amount of this. And what do they want? They want speed. Particularly, they want low latency. So the TLS protocol that we had up until just the last year or two is slow to set up the connection. It's perceived as expensive by site operators. So everyone I know who was building websites 10 years ago said, first I'll build it without TLS, and then if I have to, I'll add SSL on the parts that the security people really make me do it, right? Username and password, and then we're going to pop you right back out of that for the rest of the checkout sequence. So the big site operators have been in pushing fewer round trips times for lower speed, higher speed, lower latency. At the same time, there have been a set of, let's call them crypto warriors, the people who in the 90s had issues and concerns about principally US regulation about cryptography, who are really concerned about some of the revelations that have come out about principally US counter-cryptography over the last couple of years. I could put Snowden's picture up here, but it makes it hard to deliver this talk to a lot of audiences, right? The counter-Snowden people don't want to see his picture on things, and the pro-Snowden people think that there's privacy reasons not to put his picture on things, whatever. So the crypto warriors have been in pushing for changes in the cryptography to resist principally NSA interference. And there have been a set of pragmatists. Those two down there are Hugo Krawczyk and Kenny Patterson, two professors who've been, let's see, what can you see? Oh, there's screens back there. So if you're in the wall, you can like look straight up and see the talk above you. Otherwise, we've got to work on this. All right. Who've been pushing for taking the revelations and the research work of the last couple of decades. And the core idea here is, what if we took the things that we know are terrible ideas and removed them, right? And the hope from all of these people coming together to advance TLS at the IETF is that we might be able to have just about everyone getting these benefits together by the middle of 2020, right? About 19, 20 months from now, we're hoping that we ought to have everybody getting these benefits. So let's review where TLS came from. This is a TLS 1.2 handshake. This is the best crypto you could run in a typical internet setting a year ago. Starts out with a client on this side. Client says hello. maybe it announces the site that it wants to connect to. But that's an extension. It's not even required. That's why you end up consuming an IPv4 address per TLS website you want to run. Because if you want to put multiple sites on one address, you need to be able to rely on getting that server name indication. And the protocol doesn't require it. And until only a couple of years ago, most Java and Python clients, the curl client, that sort of thing, wouldn't send that, right? Chrome, Firefox, Safari, they've been sending the server name indication for years, but the command line and API clients wouldn't. So we're burning IPv4 addresses, right? Akamai's got a couple thousand points of presence for its TLS customers' websites, so we're burning a couple thousand IPv4 addresses per site. That made us some friends at the IP registry authorities, I can tell you. So optional server name indication. The server says back, oh, hello, here's my certificate. Optionally, a key share. If you want forward secrecy on the connection, the key share comes back. The client sends its key share. If there was a server one, that's a Diffie-Hellman key share. If not, this is just an encryption of the pre-master secret, right? So it's just what's going to be the session key, RSA encrypted to the key that was in the cert, comes back. Change cipher spec is an arcane detail of old-style protocol implementation, and then finished. The finished message is important. It's got a hash of the whole transcript of everything up through here. And that's really important for authenticating that this whole handshake happened all coming from one set of participants, and that you don't have an extra server involved in that or an adversary involved. Same thing comes back from the server, change cipher spec, we're agreeing on how we're going to talk, we're finished, and now you can do application data. How many round trips do you need before you can talk? 1 round trip, 2 round trips, and it's not safe for the client to pipeline in an extra, like you might imagine if you just want to get slash, it's so tempting to just stick a get slash in here, right? You know what the key's going to be because you're not doing Diffie-Hellman. You could just encrypt that and send it in here. And if you do, it's dangerous. Until you've received this finish message, you're not sure that what you've gotten is actually enough to compute a session key and proceed. You're not sure that get slash is going to go to where you think it's going to go. And so if it's get slash and here's my session cookie, right, quite common pattern, you've really got to worry about what's going to go over there. You've got to wait for that second round trip. Here's the best part. There's an extra round trip ahead of this to set up the TCP session, right? The SYN and the SYN-ACK come back. And there's not a standard TCP implementation on Earth that can fit all of that into the initial window. So the server can't even necessarily fit all of this in without waiting for an ACK from the client. And so now if you're talking about a transoceanic TLS setup, you're easily going to exceed 1 second just to get to the setup before you've even sent your get slash. Right now the window's larger and maybe you can get your page started within 2 seconds, but you're easily over 1 second for typical cellular and long-haul TLS setup. That's awful. We got to fix that. So watch carefully where this stuff goes. In TLS 1.3, the handshake looks like this. This is the standard handshake. Oh, I should have taken the square brackets out. Oh, I'm so sorry. Now, that server name indication is required by the standard. So now it's helloexample.com. Now we can stop burning all those IPv4 addresses. The initial hello has a guess about what crypto suite the other side is going to insist on. Right now, there's only one standardized, so that guess is really easy. And there's always a Diffie-Hellman key share, right? There's going to be reasons we're going to want to change that guess later. There's always a key share. The server comes back with, hello, here's my certificate, here's my key share, here's a hash of the transcript, and now you can exchange application data. The client's still got to wait for that finish to come back to be sure that it has a fresh key with forward secrecy. But if it has something that doesn't require forward secrecy, like get slash and a session cookie, it can stick that in its initial message. So the server's message can be finished and immediately pipelining in the response of that page. So now you've got your initial TCP setup, 1 packet out, the get slash and the session cookie are in there, and the data is immediately flowing back as quick as can be. With the TCP fast open standard, that's also become usable because of some kernel changes in Windows and in Linux around the same time, you can even have this be the final ACK or even part of the SYN. So you can now get TLS connections set up as fast as you could get a UDP quick crypto set up just a year or two ago. In a way that's standard, in a way that works not only with Chrome and Google, who have tight control of both sides of the stack, but in a way that everybody can interoperate. We've got one handshake or zero handshake setup. Now, the early data's got some dangerous bits. We could talk more about that later. That early data, this packet is replayable. So get slash and your session cookie is a perfectly safe thing to put in there. Launch the missiles, probably not a great thing to put in there unless you're ambivalent about how many times that's going to get executed, right? Well, no, so this is a real issue, right? You're not, browsers end up making this mistake a bunch, engineering choice. What's safe to repeat? If I type a URL into a browser and I hit enter, and the browser tries to make a TCP session and the SYN is dropped, right? Because again, that might all be in with a SYN. That might be the first packet. It's dropped. It's dropped because I'm on a cellular connection or something, right? Or I'm sitting in an airplane over the Atlantic. And that packet is dropped. My browser is going to repeat it. For a whole bunch of UX reasons, it's not going to insist that I hit a reload button. And even if it did, I'm just going to keep clicking reload until my page shows up, right? Same we all do. So the browser is going to do a bunch of that for me. That means that an adversary can let that go through, kill the response. The browser doesn't know that it got through, right? So the browser just doesn't see this because the adversary is muting out this part. And the browser is going to continue to generate perfectly legitimate packets like that over and over again, trying to get the page to work for me. It'll time out after a little while and decide that, like, I don't have an internet connection or something. There's no uplink. But there's a whole bunch of reasons why a perfectly conformant normal browser or IoT device or app is going to end up generating lots of repeats of that. And so there's a lot of care that has to get taken in the engineering of how to handle that early data in a way that isn't going to really screw up. One of the most dangerous things you can do, and incidentally, the way that Chrome is handling this, is just splice this early data onto the application data. Pretend it's all one stream. Make it one easy to handle stream so you just have your API reading from that. We'll get to more of that. So you'll notice that there's no finished coming back the other way. Here's why. What actually this looks like is this. Wait a minute, there's a second handshake there. Where did this come from? Right? Why is this chain cipher spec here? How come the server's now saying all of this, hello, let's use TLS 1.2? Here's the worst thing I've seen in decades of internet standards engineering. We went to roll out TLS 1.3. We got the NSS library that's used in Mozilla updated. We got OpenSSL ready to do it. We got Chrome shipping against boring SSL. We had servers working. We had Nginx and Akamai servers working. Everything's ready to go for TLS 1.3. We start rolling it out. And what do we see? Like 15–20% of connections are failing. Why? I mean, from like all over. Connections in coffee shops are failing. Enterprise connections are failing. What's gone wrong? The clients are running the right software. The servers are running the right software. What else could go wrong? The NSA, you know, it might have been. I kind of blame them for everything. Yeah, there's these things called middle boxes, right? If you ever go into a data center and you see a rat chewing on one of the wires, you're going to treat that a certain way. And if you see a box with the Blue Coat logo on it, I might make some suggestions about, all right, there's these devices from Cisco, from Blue Coat, from Juniper, from all sorts of folks. I should have asked this 10 minutes ago. Is there anyone in the room who makes middle boxes? Because I'd love to chat about what we could do about this. I don't hate you, but I hate the things you shipped 10 years ago. The truth is the new versions of this don't have this problem. But here's what we ran into. With the old version of that, we'd say, hello, and send the TLS 1.3 handshake packets. There'd be things on the wire who'd say, oh, this is a TCP connection on port 443. I guess it's going to be doing some TLS. And they would start looking at byte by byte what's on there. Well, back in the bad old days, every connection up through here has the first couple of bytes, right? So everything from 1996 through 2016, it's the same first 10 bytes starting every TLS session. So every middle box that's shipping in there, like a security device that's looking for flood data, right? Someone's going to flood you on 443. They're going to send something that doesn't have that uniform handshake everybody's been using for 2 decades. So somewhat legitimately, these security device vendors shipped something that looked at those first bytes and they said, The hell is this? TLS 1.3, there's no such thing. Whoops. And they'd kill the connection. They'd forge a reset. Right? Just like the Great Firewall of China, they'd forge reset connections both directions, and the browser would have to fall back to 1.2. So now we're wasting multiple seconds on that, and instead of better latency, we're getting worse latency and no better security. What the hell? For like 15–20% of connections. These things are ubiquitous, right? Because even if you don't have one of these in your home connection, and in fact there's almost certainly not one of these in almost any of those high-speed home connections Tom was talking about. There is almost certainly one of these at your employer, and here's the best part, there's almost certainly one of these at your coffee shop and at your hotel, because the kinds of ISPs that marketed to those places use these for security. Why? Because who knows what computer shows up in the coffee shop? There really is legitimate risk of someone showing up and doing floods or spam or whatever from coffee shops. And they've got to keep the spammers out. So these middle boxes are ubiquitous. What do we have to do? Now the public protocol version still says 1.2, and later on in an extension to the handshake that's encrypted, we can say, psst, secretly we're going to talk 1.3, is that okay? Right? That means, and then those middle boxes got all upset if their model of the state machine didn't work right, and they were looking for the change cipher spec messages. And if they didn't see those, they started really freaking out, and they'd kill the connection after a little while, right? We made this change, we shipped it, and we'd say, all right, the connections negotiate well, we get the get through, we get the response back, and like 10K in, it cuts off. Everything's getting reset, what the hell? The middle boxes are getting confused and frustrated that the state machine's not working, so now we send a change cipher spec message that's empty, it doesn't do anything, both sides ignore it, you can put whatever you like in there. There's some neat ever cookie work on seeing whether we can now use that to track people by what goes into the change cipher spec messages. That's a different talk. We're looking to see whether we can stop you from tracking us with that, but all the same. So this is what's actually shipping. And that ruthlessly practical issue of we've got a better protocol, everyone agrees it's a better protocol, now can we actually get it deployed? That's what's been occupying the last 3 years of IETF time. That's been years of hard engineering work to figure out what's going on, to run the tests, to repeat the integration testing as we figure that out. And we've tested it in all the environments that the participants know about and think are interesting. We all work for universities or Google, or we're really nervous that we're not seeing widely enough, and that's part of why folks like me are out here doing the pitch of, come play, we could use the help. All right, so that gets the speed stuff. What do the pragmatists get? As I said, what happens if we just throw out all the stuff that we've known for decades is broken? Oh, well, the code gets simpler. There's less room to hide nonsense like Heartbleed in there. There are probably new protocol bugs, but we'll handle those as they come. What do the crypto warriors get? First off, RSA key exchange is out. Everything's now elliptic curve Diffie-Hellman key exchanges. That's fantastic. Why is that fantastic? Forward secrecy is great against passive adversaries. That is troublesome. Why is it troublesome? The same sorts of people who here has a TLS tap in their environment, who knows about it, who's actually got like an enterprise environment that's tapping client or server TLS? Yeah, okay, thank you for admitting it, good. There's a bunch of folks who said, well look, I can extract my server key and then I can set up a passive tap that can tap all the client conversation with that server. And there's a lot of reasons in a regulated environment, like a bank or a hospital, that this might be an apparently reasonable choice of how to do your engineering and how to designate a trusted tap that's looking for security information on your enterprise network. It's a terrible idea, but there's a lot of reasons why it may be the least terrible idea of the available implementation choices for a hospital, for a large bank. It's no longer possible, and we're going to have to find new ways to do it. It's going to have to be an active proxy now instead of a passive tap. Those folks have spent the last year delaying the launch of TLS 1.3, asking to have RSA key exchange put back in. They lost. They got told, do it as an extension or something. We'll work it out. A whole bunch of the knobs and dials for funny crypto are out because we're too worried about most of the choices you can make there are bad, and if someone comes to you and says with a sort of a Middle East Coast US accent that they think they've got a better idea for you, maybe we should be suspicious of why they're giving you that advice. The NSA is based in the middle of the East Coast. Big number DSA is out. Old bad crypto, it's a terrible idea, it's a horrible DOS risk. Much more of the handshake is encrypted now. So much more of the ability to fingerprint passive traffic is out. A Chrome on a Windows laptop doing a TLS 1.3 connection and my iPad doing a TLS 1.3 connection should not be distinguishable from the TLS handshakes. Those ought to be identical because we want them to blend in from the point of view of a network tap. DJB is a three-letter acronym that is not NSA. He's a guy. He's a professor in Chicago and in the Netherlands. And he and his colleague Tanya Lang have been pushing a development of cryptography that is on an entirely different mathematical basis than the NSA NIST crypto that we've been using, the RSA and the elliptic curve Diffie-Hellman work on the P256 curves. Totally different cryptographic basis, totally different mathematical basis. I'm not saying it's any better, but it doesn't have the same bugs and it doesn't have the same backdoors. And so for folks who are concerned about some of the secure random work from a couple years ago about bad elliptic curve random number generators, you could use Dan Bernstein's crypto. Maybe it's better, at least it's different. For those folks who are concerned about all of the horrible, horrible TLS bugs around cipher block chaining, we're making a lot of changes to make it harder to screw up while implementing the spec. It's not impossible, I swear. But as someone who started as an undergrad trying to implement this stuff, my heart goes out and my sympathies go out to all of the grad students and undergrads who are going to try to implement this. There's a lot more attention to how to build it safer. Here's test points that you ought to be able to run through some of your intermediate functions to know that you built it right. All right, therefore, are you all sold now on TLS 1.3 is going to be great for you? Faster, safer, better? I'd love for you to all go try it at home. But I feel obliged to put a few little warnings on the side of the bottle, right? That if you have a heart condition, you should maybe wait on deploying TLS 1.3 and let some of the rest of us discover that like it doesn't work when the time zone changes or something. In particular, if you're a heavy user of client certificates for web authentication, the ways that HTTP and SSL mangled that together changed dramatically for TLS 1.3. By all means, go and test, but you should not expect to be rolling it out in the first half of 2019. Specifically, if you use client certificates in a renegotiation mode, where the session starts out without client certs and then midway through wants to upgrade. The overwhelming majority of folks who are using smart cards and CAC cards and that sort of thing are in that world. You folks should not be trying to deploy TLS 1.3 right now. We're going to do something for you. It's going to work great. It's going to use HTTP 2. It's going to be beautiful. But you're going to have to replace every piece of software you use. No big deal. We're going to get there. The vendors are on board, right? That's really going to work. If you're a heavy user of middle boxes, particularly in the passive tap mode, or if there's anyone here who's ever shipped a DSA key in production, I'd love to meet you and hear why. But if you're using either of those, there are operational issues that here you're not going to use those. If you're, for whatever reason, using session key export, which is what you use for those passive taps, again, you're going to want to wait. If you don't have to wait, and let's do a quick check, who here has got any of those going on in their organization where you should wait? Because I do. I got some client certs. I got a bunch. 1, 2, 3. Yeah, there's maybe 5 of us in a room of 120 people who should probably wait. We can test in small ways, but we've got to be careful. For everybody else, if you're using the ubiquitously common Nginx web server, you should make sure you have the latest version of OpenSSL, at least 1.1.1. That's easy to remember, right? You change the line in your configuration that says SSL protocols TLS v1.2 to say v1.3, and you ask the server to test your configuration is good. If it is, if that check passes, you will interoperate with the TLS 1.3 that is in Chrome and Firefox today. It's just that easy. You can really try this over lunch and see whether it's going to work, maybe on a staging system before production. And the new OpenSSL 1.1.1, that's the one that's being presented for standards compliance and common criteria evaluation in the EU and in the US, and is going to hit all of the lovely regulatory checkpoints for deployment in financial services and government sectors and that sort of thing. So we're working to make this as easy as possible. You know what's not up here is changes to your cipher configuration, right? Everybody who's set up a web server like this has ended up with a page of saying, well, use AES, but don't use MD5, and I want to use elliptic curve Diffie-Hellman, and they've tried to, like, oh, if it's a mobile device, support cha-cha, but otherwise don't, all this kind of nonsense. I'm seeing nods from people who felt this pain. You know what the best thing is about the way that OpenSSL and Nginx and Apache and all the rest are supporting this? It ignores that for 1.3. The way to specify the cipher strings for 1.3 is so different, and there's only 5 standardized anyway, and 2 of them are bizarre and no one's ever going to use them. And these 3 come in a nice order of like good, better, best. That it just doesn't bother exposing a configuration interface for most people. It doesn't use the old one. You can put whatever you like in the cipher string setting, and it'll use that if it negotiates 1.2. But for 1.3, you're just going to get sane choices. Enjoy them. There is a configuration option I'm not going to tell you about that you could use to hurt yourself. I recommend against it. It's in the man page, right? Okay. If that works, there's a handful of things to test. Like, does the server actually run and start? Can you fetch a page? If it does, and you really want to upgrade your whole infrastructure, getting the web parts working is easy. The biggest consumer of TLS on the internet today is not the web. It's email. Every email connection is using opportunistic end-to-end crypto, hop-to-hop crypto, excuse me, for every piece. And that is harder to debug, harder to notice. What you often, if you try upgrading this and you get it wrong, you will notice because now, like, you can't receive mail from Hotmail. It still works with Gmail, still works with your local university, but now Hotmail doesn't work because you picked the wrong cipher or they don't support the kind of TLS negotiation you did or something. Or all of your clients will work except for Android before version 5, right? And so testing the SMTP and IMAP issues is way more of an interesting problem than the HTTP version. There's only a handful of HTTP server makers. There's only a handful of HTTP browser makers. And we've all been spending our time in the same rooms doing round-robin interop testing. The web parts of this are going to work fantastically. The rest of your infrastructure, your voice over IP phones and your email and that sort of thing, those are going to be the places where 1.3 is going to be exciting. And I look forward to working through that with you. The other big thing to test, even just in the web session setting, is where does that early data go of where your app framework, if you're using Rails, if you're using TurboGears, if you're using Java, your app framework has opinions about what to do with early data. They've already shipped them, and you should check what's going on with that in your environment. Broad set of clients, that's fine. They're updated, they're ready to go. Everything I've named there already ships with TLS, well, not Java 6, ships with TLS 1.3, and you can go try it now. So let's see if we can see the future. If this goes well, I get to advance the slides. There we go. If this goes well, every one of us is going to be benefiting from 1.3 on our phones, on our computers, in our enterprises in 2019. All the fast cycle browsers, you know, the Chromes and Microsoft Edge and that sort of thing, will be ready in 2019. And I'll be helping folks launch e-commerce sites that are 1.3 only tail end of 2019. Plausible to drop 1.2 the following year. This is my optimistic hat. Now, I'm a security professional, so I don't typically live there. The other possibility is that there's someone who knows exactly how bad TLS 1.2 does, and they're waiting on 1.3 being available before they tell the world, right? Think like how 2014 was between Triple Handshake and Heartbleed and all the rest, Poodle, the things that caused us to crash off of SSL3 hard in a way that broke sites, in a way that hurt people. That possibility for 1.2 is still out there. Could be. We should be prepared for that. In that world, basically all of the crypto software that we're running, all the computers in this room need patches. That's going to be an exciting and unpleasant world. More plausibly, we're somewhere in between. In that world, IETF ships a handful of extensions to make adoption easier. In 2019, TLS 1.0 and 1.1 get deprecated. That standard's already going through. Standards like delegated credentials that let other protocols interoperate better. Exported authenticators, which is what you need for all those client certs, those half dozen of us who raised our hands. We get what we need in 2019, and then in early 2020, we can start making the switch. And by 2-3 years from now, we're in a markedly better place. I'm going to ask for questions in just a moment. The first question I always get is, but what about all the post-quantum crypto? So I've decided to answer it in the talk. Post-quantum crypto is great. You've got a number of lovely choices. We're beta testing some of them now. There's several great choices you can make called things like ring learning with errors or hash-based signatures that are fantastic against quantum computers. Many of them can be broken by a Nintendo. So we're working on that. Right now you want a mix if you want a classical algorithm and a post-quantum algorithm paired. The problem is that for the post-quantum algorithms, either you have a number of horrible choices. Either like it takes a kilowatt hour to encrypt something, or your keys are all 5 megs long instead of just a couple thousand bits, or every time you encrypt something, you flip a couple of coins and maybe it's not decryptable by anybody, but you can't tell. That one's really weird. Or a signature, there is a great system that ignores all of those problems. It's fantastic, but you only get one encryption per key. It's the post-quantum version of one-time pad. Happy to chat more. Lots more standardization going on that. So here's my advice, is experiment with 1.3 now. At least make sure all your systems are running 1.2. If you're still supporting 1.0 and 1.1 somewhere in your infrastructure, it's really a great time to stop that while you can. Take a couple of weeks and do it in a planned and deliberate way, or we can talk in February about how to do it overnight. You can pin certs where you can. Certificate authorities are great for environments of low trust, like the public internet. But if you're dealing with a CDN or with Amazon or some major infrastructure provider, you can probably pin certs and be detached from the certificate authority infrastructure. I bet you'll enjoy that in a couple months too. And we can turn off all the old stuff. All right, thank you folks for your time. I think we've got a couple of minutes to squeeze in some questions. I've stunned you all, awesome. What?
One question on zero RTT and replay attacks.
Yeah.
What is your recommendation on that one? Like protect yourself with high layers of the stack? Or?
Okay, so the question's about zero RTT and replay attacks and what could we do about it? I'll tell you what I'm doing about it is I'm shipping with zero RTT disabled, and I'm reading the newspapers, and I figure I'm going to let somebody else experience the first 6 months of zero RTT in the wild. There's plenty of places that are only running one website and so can afford to take their chances with that. We've got a couple tens of thousands, and so we're gonna let that wait for a bit. Particularly there's questions of zero RTT integration with proxies, of when do you pipeline the zero RTT data into, how do you encapsulate that to mention if you're repeating the request for some reason upstream? You're still giving me a look as if I didn't answer the question, so perhaps you could repeat it.
Okay, so the question is because obviously replay attacks, right? For example, for HTTP protocol, for HTTPS protocol, it's quite easy to protect yourself against that because of all the CSRF tokens and all this stuff, right? I'm just wondering how would it work for the other protocols?
Oh, for non-HTTP, zero RTT is only there to make ads load faster in Chrome. If you're using IMAP or SMTP, I think you've got no business using zero RTT. Right, the question was, what about the non-HTTP protocols? You made a claim that it's easy to protect yourself against replay with CSRF tokens and so on. I'm not sure I believe you. Like, it seems like it ought to be, right? But we've done a couple of cycles of working with academics to generate proofs of security for zero RTT with a CSRF token and in another context. And we keep getting surprises about, well, that's mostly good, but look, here's this novel way the protocol can fit together and where something gets repeated or dropped in a way that is surprising. It's not as bad and surprising as TLS 1.0 and 1.2 renegotiation when you added client certs, but it's not as bad as triple handshake, but it's still, that's funny. And so that's why the standard for how to do this is still in some amount of flux. So there is an RFC that will tell you to do more than just CSRF protections as part of rolling out HTTP on 1.3 with zero RTT. If you're not using HTTP, how do you use zero RTT? The benefits are slight, and I would advise caution. There's years to wait and let somebody else see and then turn that on. Thank you. Yeah?
You said that compression would be removed from version 1.3.
Mm-hmm.
The question is why does it relate to certificate compression and why is it dangerous?
It's not just certificate compression. The reason is for a lot of TLS, for the TLS and web context, what web servers often do is assemble a body out of server-generated content that might contain secrets like CSRF tokens and user-generated content like a post. So if you ask something like gzip to compress that, what does the gzip algorithm do? It looks for places of commonality and it changes the size depending on how much commonality you got. So if you imagine a piece of server-side JavaScript, let's say there's a cross-site scripting injection attack on some site, I can inject some JavaScript that'll run in your browser. It can generate a whole bunch of requests. Each request will be annotated with your session cookie and then sent for compression. So it can try a whole bunch of guesses for subwords of your session cookie. And where it gets a success, the request is then shorter because it compressed better. So there are these lovely, lovely attacks that let you use compression, what's called a compression oracle, to try to, you can only write data and read the size or the timing, and you can use that to read off secrets that are also embedded in the same communication alarmingly fast. It's magical when you see it work. And so that's why the old advice in the 90s was always compress your data before you encrypt it. Why? Because by compressing it, you remove duplication. So you're maximizing the entropy before you encrypt it. In World War II, if you're Alan Turing, that's a fine idea because your compression is only so good and your encryption sucks anyway. If you're not using a machine with rotors and a pegboard, this is not a good piece of advice because a modern encryption algorithm ought to be able to encrypt a uniform megabyte of zeros as well as it encrypts a random megabyte of data. So the compression, the idea that, well, we're optimizing our entropy that way, that hasn't been true in decades, and you shouldn't do that. It's not helping you, and it exposes these compression oracles. So the TLS level compression is now out for 1.3. Thank you. Yeah?
So what about those passive tabs or the intercepting traffic? What if I must see the content?
What about passive taps if you need them to work, if you must see the content? You've got some interesting problems, huh? What we've seen out of that for folks who need some kind of a tap is a couple of options. One is to use a TLS library that does allow session key export. So you might be able to get your server to log session keys in some low latency way in a way that makes them available to taps. You might get your client to do so. I've even seen some devices that use CIPSO, the commercial IP security option, to adorn TCP packets with the session key of the TLS data that's there, right? So from a security point of view, or from a secrecy point of view, this is a terrible idea. You should make sure your outbound router is stripping the IP security option, but you wanted that anyway. So you might be able to work something out so that your F5 load balancer or whatever is terminating TLS with 1.3, but adorning the what's that? I'm sorry? Or it could be an active proxy, right? So an active proxy works fine if you want to log all the data or run your intrusion detection or intrusion prevention software and so on. That could work fine. Active proxies are fine. The problem is we've got some colleagues who say they really need passive taps to work, and they really need, the fun ones say, but I really have to deploy standard Chrome on this side and a standard closed source web server on that side, or like a Windows, IIS or something from Microsoft, and a Microsoft IE or something over there. I really can't modify those. I need them to be the TLS terminators, but I still need to tap. Those folks are going to have a hard time, and my current belief is that their have-to requirements are not as absolute as they might say. Like, there's a $10 million for recertification or so on cost, but they're not absolutely hard. They're stay on 1.2 for now, and we're going to have to work on recertifications and building up a tech stack to where we can help those folks.
Does it apply also to SSL inspection or just passive?
What do you mean by SSL inspection?
Transparent inspection of SSL traffic going through the proxies, which are transparent.
What do you mean by transparent?
They are not configured in the browser.
If that is looking at the out, can it decrypt? Woo! Okay, right. Those devices have been declared an enemy of the IETF, and the people who build the internet have decided to break them all. Yeah. Not only is there, will the existing ones stop working with 1.3, because you've got no way to get the decryption keys to them, right? Because everything is now forward secrecy with Diffie-Hellman negotiation. When I talked about middle boxes, those are exactly the ones that I meant. And there's a consensus-based, agreed-upon standards from the IETF that those are a tool of Orwellian evil and must be broken.
What do you really feel?
That's not my view. That's the IETF view. I've worked on those things before. I don't think they're absolutely evil, but I want to acknowledge that the IETF has decided they're not going to work on the internet. If you disagree with that, you can come to the IETF with me and we can have some, I'm serious, there's engineers there who are willing to have practical conversations about this. I'm not sure that I consider those opposed, but security versus privacy. So partly, there's a bunch of folks who were using devices like that to hurt people who were just running a browser and wanted to talk to Facebook or something, right? So if I buy a new device from the store and I try to load up Facebook, I think we can all agree that nobody should be able to tap that. On the other hand, if I'm running a bank with a call center and I've got a bunch of people who are low-wage employees taking phone calls from people, I think and working on a company-owned workstation, I think we can all agree that the people working on the company-owned workstation ought to be subject to taps by the company to make sure that its own security goals are met. They have no privacy interest in the work that they're doing for somebody else on that. There is not a great tech answer for that second case right now. The IETF prioritized the first side pretty strongly, and there's absolutely an open environment for talking about key extraction or session key extraction for that second case, but it's not in the standard now, and that's an area where work is welcome. Right. In an enterprise environment, if you want to tap the devices in your enterprise, one option you have is to not do TLS on your internal network and do it all at the edge. That's not a great idea, because now you end up with sort of a Chewy center problem. One option you have is to do that all, but configure your server or your client to dump the session key for logging purposes. And one option is to set up something like an active proxy with a proxy pack file or something, where there's a device that is, so you put a special cert on all of your devices, a CA on all of your client devices, and you have an active proxy that's intercepting. That'll work fine. That works fine, but that requires the owner-operator of the client machine to accept the new certificate authority, and well, they get what they asked for. Well, at the point where the operator, no, wait a minute. It's implied by the word transparency that the client is going to make a decision to install this chip in its head? Yeah, then it's going to work fine. So you deploy your new CA, you put your active proxy in place, that'll work fine, that's fine. Although, you're going to want a software update from your proxy vendor because that early data issue is still real. And if they get that wrong, we've shipped a couple of betas of that and we've hated all but the last one of them. If you get wrong the integration of the early data with the rest of the data stream, upstream web apps will misoperate and you won't know why, and it's hell to debug. So watch carefully if you are in that environment for those updates. They're going to help. Cool. We're way past time and we got to wind up. Thank you so much. I'll be out there and happy to take other questions in person.